So welcome to the last talk of our first session here, UGM 2021. Next title is the Research Data Management System at University of Groningen, Architecture, Solution, Engines, and Challenges. This is going to be Strikwerda starting off, and then we've got two other speakers after that. So I'll let him hand off when the time is right. Take it away.
Yeah, okay. Thank you for having us. So we're going to present our research data management system we use at the University of Groningen. RUG is an abbreviation of the University of Groningen. So the RDMS is like the research data management system. So we're going to present to you the architecture, the solution engines, and the challenges. This is our team. It consists of several developers, developer, sysadmins, and people that do the support, and of course some managers. This is a map of the Netherlands. Groningen is on top of the Netherlands, like Utrecht is in the middle, and Maastricht is in the south, Amsterdam is over here. In Groningen we have a university. It's a pretty old university. It was founded in 1614, so it's like 400 years old. Also for Dutch standards, it's pretty big. It has 34,000 students, 400 professors, and we even have a professor with a Nobel Prize winning. And this is the agenda of this talk. First, I will do the storage architecture. Andre will talk about the application design, the web interface, and Simona will talk about the IRODS rules, the custom policy engines, the metadata templates, and the auditing. And we close with a what's next and a Q&A. So storage architecture. This is the why. Why do we have such a system like this? It's because we want to have our own Google Drive for research data. The researchers want to have their data on premises. And it's an object store instead of an old school file system. People really like the self-service part. So they can set their own ACLs on their own files and they have full control over their data without bothering the help desk. And also they can update and add any metadata they want to their files. We have home data, group data, and project data. The file access is audited via RabbitMQ, Kibana, and ElkStack, and all files are replicated, 2 copies spread between 3 locations. And that looks a bit like this. Here you have the users. Here you have the interfaces. We support 3 interfaces: the web application, the WebDAV for uploading and downloading files via Windows, and the IRODS command line client to upload and download files via Linux, for example, via HPC. The interfaces connect to a load balancer, and behind the load balancer we have 3 iCADs. We have 3 because we also have 3 data centers. The iCADs share the same database cluster, and also we have 3 big storage systems. In every data center, 1 big storage system. And the storage system has a big local disk of 700 terabytes with a ZFS file system. And on top of the big storage systems, we run our resource virtual machines. And those are 60 terabytes each. And for now, we run 3 on one server and 3 on the other and 3 on the other. And we also have a tape archive, IBM Spectrum Scale tape. So we can move the data from disk to tape. This is a picture of our big storage system. It has 90 disks, so it's pretty badass. It runs Ubuntu with the CFS file system. And the CFS file system has some nice features like data deduplication, compression, and self-healing options. And of course, it has redundancy built in. Here you can see the size of the pool, allocation, and free. So we're now at 15% capacity. And everything is still healthy. We have different IRODS zones. IRODS zone is like an environment, like a private environment. So we can have groups and users using their own private part stuff. So for the RUG, we have our own university zone. For the UMCG, we have a special zone. This is from the hospital, the people that are doing genomics. For SRAM, we have a special test zone. And SRAM is the system we use for the SURF research authentication manager that basically allows us to get external users on our system. And of course, we have a test zone and a developer zone. And if we want to add extra zones, they're really virtual machines, so they can run on the same infrastructure. So we don't have to buy new hardware. We can run zones, multiple zones on the same infra. RDMS is RDMS backend is supposed to survive, or is designed to survive broken disks, broken volumes, broken servers, even a down data center, maintenance, of course. The resource virtual machines are small, so we can move and migrate them if needed. It can support scalable workloads, and also it can support our high-performance computing workloads. The authentication is based on PAM, pluggable authentication module. It's pretty normal for Linux standards. People log in using their email and university passwords. And we can use the RUG LDAP, which is from the University of Groningen. But also we have a special container with the SRAM uses for external users. And it looks a bit like this. Here we have the data manager in Groningen. The data manager is able to create the user in the SRAM portal. They store their stuff in an LDAP server at SURF in Amsterdam. From there, there's a one-way sync to our container, our own SRAM container in Groningen. And here we do some enrichment. So we put some extra attributes like a password field. And here we have the normal RUG LDAP user. So basically our ICAT can query the SRAM users and the normal RUG users. So for example, somebody from Utrecht can log in via the VPN to our system and they can see the data from us here in Groningen. And here are some security best practices. Pretty obvious things like don't allow root SSH directly. We have second layers of firewall. We have the host-based firewall, but also network-based firewalls. We have our own intrusion detection system. It's called Stealth. We do filter ban on WebDAV. And it would be nice to have a filter ban on iRODS. I'm not sure if that's possible. And we have a monthly security audits by our own security team. And an external company does some pen testing yearly. So that's the way how we keep things secure. And that's it for me. So now Andre can take over. I will stop my share. Andre, it's you.
Yes, thank you. So let me do. So the application design is part of my talk. And basically the application design that we tried to achieve was the modularity and as much possible the abstraction. We reached this till some degree. And the base idea to split front-end, mid-tier, and the backend and iRODS as the services and the different containers in a closed network environment, and to support the vertical and horizontal robust of the system. So what we have is the Nginx on top of everything. So it's like a proxy and request forwarding. And then behind the proxy, we have a closed network with the mid-tier web service, mid-tier database, and the logging service. So all these services are practically RESTful-like. And on top of it, well, inside also there is an iRODS web service that's also RESTful, like the API that we run on Jargon and Tomcat at the moment, but we have a plan to migrate to Python. And all this we have, the rest we have in Python, but basically it does matter the technology. We try to make it technology independent, at least on the logical level. So, and then there is an ICAT and resources and all this backend nice stuff that Ger just showed. So apart from that, we have another way to access the iRODS, and this is the standard tools like command line interface, WebDAV, and others. So we want to have an NFS mounts as well. One crucial part of the system, of course, is the metadata, and we split logically metadata to two parts: mutable and immutable metadata. So mutable, we call those that users can generate themselves. They can put wherever they like through the command line interface or through the web interface that we offer. And immutable metadata is something that system generates automatically one way or another, and we use that to control the workflow inside our model. So for instance, the immutable metadata of IDs of metadata that were automatically extracted, or system metadata that we added here and there by the needs of the workflow management. So our web interface, when we started to develop, it was not like that as you see on the screen, but then we've drifted more like to the drive philosophy, and we tried to add functionality to offer the functionality for our users as the drive, so they can do most of the things through the web interface. So far, we do not supporting the upload, but that's the plan. And basically, we do have projects, we do have groups and team drives. We call that as like shared part of the system. So on the previous slide, you see that I am on my home folder, but basically, we do have as well the groups and team drive support and projects which are specific areas to workflow management. So on the interface, we have object tree on the left, files, folders in the middle, and then we have object information when you click on that on the right side. Basically, there are right-click menu that allows to do operations on the objects. And for instance, if you do extract metadata thing, so what will happen, it will start the background job, and we have a system using our mid-tier database to control the status of that delayed rule that is executed on the iROT side. And when it's done, so you can see straightforward the extracted metadata automatically from the file if there are any. At the moment we support JPEG, simple DICOMs, Word, PDF formats. But because it's all Python, so we can just add any format by the user requests. So also we have a set of rules on our system, and these custom rules are delayed rules and monitoring. Also, we can copy data with permissions and metadata. So these are the rules that can be executed, and you have flags that to say how you want to copy that data. Automatic metadata extraction, and we do have a custom policies engine that I'll talk a bit later, and audit and permission control extra rules that those will be also described a bit later. And we do have rules to support tape library archiving, and we have dedicated project for that to test how it all actually works. So custom policies engine. In scope of our system, we implemented a specific set of key value unit syntax to attach to the data object like file or folder. And that is name with the hash, so prefix and hash, and the JSON inside the value, and then unit to control the status. For instance, the actual example can be like that. So generated hash, policy project to run, and the username, which needs to be actually the username that must run that policy. And then we have data object, policy metadata, and in mid-tier we have a registration of that policy as well, key and unique hash value to control the code injection, so that when we add the policy, it should be immutable, and no malware code can be injected into that value. So we have a table that controls that inside the mid-tier. And that's the how it looks like inside. So the object and hash and the key. And before executing the policy, afterwards we check. So we have a flag to check validation of that policy. So if we can find that hash, then everything is okay. So what's happening on the backend? So we have a server cron job, a rods user, and then that cron execute I commands that queries iRods metadata for the policies to run. Then we get from that information key value unit, metadata ID, and user that needs to run the policy. And then we set the environment for that user as we are admins, and that's at that point. So we set environment for the user that needs to execute the policy and execute the rule with the metadata ID. Then using the iRods policy engine, we have iRule that parses the, actually gets the metadata ID and gets by this metadata ID key value unit again. And then it parses the value to get the function name to be executed as a policy. It's also written in Python then, and parameters for the input. Then we execute policy and update policy status. So clearly we have on the first step, when we do iRods rule execution, we can control the threading and make it like not delayed rule dependent engine, because if we do a delayed rule, then we might block other delayed rules if the policy is quite heavy, for instance, copy directory to tape or something like that. So this is the Python code that we use, like different parts of the Python code, but from that example, we can see what's happening. So we import the predefined function, we register available policy with that function, and then we run the policy dynamically using the Python code functionality. And I give floor to Simone now. The next part of it. Let me stop share.
So I hope you all see my screen. Thank you, Andre. I will be presenting the metadata template solution and the auditing solution that we have implemented for the RDMS system at RUG. So basically, why we have chosen this approach? Well, we've seen that basically the metadata templates is one crucial element in tagging the data being stored. And since we are at the university where I have several faculties, we have received several requests for metadata templates from very different research domains, from social sciences to microbiology or archaeology. Here you can think of what users would want to place in their metadata template. So you could have a template for publication where you would place information about titles, authors, or you could have actually an experiment and you would want to place information about your recording. Basically, these two templates are extremely different, but also the technical skills of the users are also very different. So users from social sciences are not as skilled as from the ones we have from microbiology. There is also not one solution that fits all the needs, because every research domain has specific metadata attributes, and even within that domain, they have different collection of tags. Also, we have received requests of importing different metadata templates from other domains. Our solution is based on, we wanted first to implement the basic common schemas, the JSON schema and an XSD schema. But we also wanted to provide a simple builder for the many simple requirements that most users have. XSD schema we have not implemented yet. We plan at this point, we have to convert to the JSON schema. These two could be used independently to create a dynamically form on the fly, which handles the validation, and data is afterwards stored in the in iRods. It's being validated and stored in iRods, and the same is done the other way around. It's read from iRod, loaded in the form and validated. So this is for the tagging. As the example I had before, you would have the self-defined structure. You could use standard types, or the users could define their own types with restrictions. And the fields would validate, the form would validate the fields on the fly. For the auditing, what we our auditing pipeline is basically similar to the standard auditing pipeline, where we have here the RDMS. I've depicted for clarity the iRods backend with the audit plugin, and this is the front end, the RDMS mid-tier. The auditing plugin pushes the data to the RabbitMQ, further to Logstash, then to the Elasticsearch. Data can be visualized via Kibana or via the RDMS mid-tier to be presented to the user. We have started this, and even because there was not much activity in the system, we still managed within a couple of months to collect 500 gigabytes of auditing data, which considering the fact that for different research domain, we need to store that data for 10 years, we realized that this was not feasible. So what we did, we tried to reduce the amount of data. We first reduced it with the PEP regex to match. That's just a setting provided in the iRods configuration JSON file. That reduced the data by considerable amount. And we also, on the level of Logstash, we have added a Ruby script which just removed the empty fields in the document. So the size of the documents are also reduced. In the end, we now keep about 5% of the original amount of data. But considering we have to store that for 10 years, that is far than enough. So we've looked further at different solutions. So what we did was actually implemented an index lifecycle management, where now the Elasticsearch nodes are split in hot, warm, and cold. So the hot node rolls over to warm and to cold. So what are these nodes exactly? Basically, a hot node is the active node where the data is being written. It's also actively queried. And it's one of the required phase in the index lifecycle management. When the size of the node, the maximum size of the node has been reached, or the maximum lifetime, the hot node rolls over to the warm stage. The warm stage, it's also being actively queried, but this data is read-only. No data is being written to that node, which means that this data can be moved to less performant hardware. When similar with the hot nodes, when the maximum lifetime has been reached, it rolls over to the cold stage, where this holds the less frequently queried data. It's still searchable, and before being deleted, a snapshot is created and stored to a long-term storage, and we are considering now a tape archive for this solution. What's next? We have presented what we have achieved so far. This is a quick, it was a quick selection of what we have achieved so far, and this is a sneak preview of our backlog. I will just highlight a couple of items. What we want to do is actually make the code open source and improve the deployments. We are looking into multi-factor authentication and external users. We want to improve the metadata templates, add snapshots lifecycle management, make an iRods NFS mount. We also have currently seven major projects running with different faculties at the university. So we want to focus into that. But it doesn't stop here. So lots to do. But thank you for your attention. And if you see something you like and you want to reach out, this is our contact email.
Excellent. Thank you. Thank you to all three of you. That was very smooth handoffs. It's great. I do have, we have one hand up. Let's see. Alan, who just spoke a minute ago, is going to ask a question. There you go.
I was just, well, you answered this in your last slide, I guess, but I was curious about whether this, specifically the front end piece, was available for viewing anywhere, but it looks like open sourcing it is one of your next steps. But yeah, it looks really good. Just wanted to point that out.
Well, we hope to make it available to public, the repository available to public quite soon. So there is nothing secret over there actually. So, but we just always, improve quality of the code here and there. So that's probably the main stop factor.
Okay.
Very good. We've got one question from Claude, I think. Claude,
Hi, Claude Fortune, CSR, South Africa. Well, the one question was going to be, is the front end going to be released into the wild? And how soon can we get it? The other thing I wanted to ask about was, you spoke about using multiple zones on the same hardware. How are you guys doing that? Are you dedicating specific volumes on a specific node, or are you guys just filling up one giant pool? How's that part working? And then lastly, can I get that last slide for that email address? Because I've got a couple of follow-up questions.
Yeah, we can also post the email address in the Slack as well.
Yeah, my Slack's not working, sorry.
Oh, okay. Who wants to answer the questions here about the hardware in the back?
That will be me.
Okay.
We run the virtual machines on the same pool, like the underlying CFS pool is the storage for our virtual machines. So the virtual machines get their storage from the pool, from the physical machine.
Yes, so I would probably add to that a multiple zone idea is that, of course, there is always the federation option within IROS. But for us, sometimes it's also dedicated to GDPR, so that medical data are not easy to federate. In this case, because we know users inside the university in this and do a PAM authentication. So for us, technically, it's not a big deal to re-authenticate user automatically to a different zone if that user is the part of the university infrastructure. So that's the idea that lies behind the multiple zones, so that there is an interface. You have just change zone button, and once authenticated, sort of a single sign-on thing, and if that zone supports that user and authentication, so it's just you automatically redirected to another namespace. Also, the thing is that if you have two mounts, WebDAV mounts on your PC at the same time with different zones, you can straightforward copy data between those folders using just a file manager, right? So, and that's what we want also sort of support, at least on the visual part for the interface. And yes, we want to deliver the interface as soon as possible, but we need to improve the deployment scripts. So far, deployment might take some effort. For the local VM, it's not a problem. You just need a Docker and then it basically runs, but we want also to have more options for the deployment.
Excellent. We had one last question. Are the VMs, they're mounting ZFS using NFS? Is the last question?
No, they're using the block storage. So they get the block storage from the underlying CFS pool.
Got it. Very good.
Yeah, but we want to implement the NFS mount for the storage itself. So for the IROS visibility for all the data. Yeah, on the client side.
Is Claude's hand back up?
Oh, I thought I loaded it, but
Okay.
could you guys maybe elaborate a bit more what you're doing with the tape, and what type of setup do you guys have? I've seen you just mentioned Elasticsearch. So is that the metadata for Elasticsearch only, or you guys dumping data into tape as well?
So the idea for the metadata templates with respect to the tape archive is actually that we want to store the snapshots of the frozen nodes before they are deleted. We want to store them in tape because they have to be stored for 10 years. That's the requirement with respect to the GDPR and the research. But they don't really necessarily have to be searchable on the fly. So that is one of the requirements. That's why we want to, and we're looking now into the Elasticsearch clusters. I think the latest version, they want to support snapshots repository. So that is why we added on the backlog the snapshot lifecycle management.
Very good. Thank you. Thank you. It's right on time here, and I appreciate it. Thank you for this wonderful, wonderful talk and Q&A. Thanks a lot.